Hello, Chemistry 12. This is Mr. Chan. And today what we're going to do is we're going to start a new topic called acid, bases, and salts. Okay. Now, so what I want to do today is I want to talk about acids and bases, just a brief introduction. Some of the stuff will be review of Chemistry 11, but some of it will be new material. Now, back in grade 10, you remember the characteristics of acids and bases. Now, acids, you remember, what would happen is they would have H plus in the equation or in the formula, and bases would have OH minus 1. Now, because of the presence of those ions, what happens is that they have certain characteristics. Like for the acids, they taste sour, they conduct electricity, they give off hydrogen gas, while bases, they would taste bitter, they would feel slippery, they would also conduct electricity. So one commonality between acids and bases is both of them conduct electricity. And that's because of the presence of either the H plus ions or the OH minus 1. Now, when an acid and base react together, they lose these characteristics, but they still conduct electricity because of the ions that are produced in the neutralization reaction. Now, let me give you a typical example. Remember back in Chem 11, your Science 10, you would have HCl and NaOH. Now, HCl was your acid, and NaOH was your base. Now, when you had the neutralization reaction, what you would get is you would get water and NaCl. Now, why does it still conduct electricity? Because if we focus on the NaCl, sodium chloride is a salt. And what happens is the sodium chloride is a soluble salt. And you recall from last unit, a soluble salt dissociates into its component ions and is able to conduct electricity. Now, one thing about acid-base equations back when you were in grade 11 is when we talked about the net ionic equation, the net equation would be the H plus from the acid and OH minus 1 from the base to give you water. That would be the net ionic equation for a general acid-base equation. Okay, it's because the hydrogen and the hydroxide both react together to produce a new substance, a water molecule with different characteristics. Now, again from grade 11, how do we name acids and bases? Okay, for a two-element acid, okay, what happens is it would be hydrogen with something, with another element. What you would have is you would start with the formula name would start with hydro and ends in IC. Hydro ends in IC. So for HCl, that would be considered a two-element acid because you have hydrogen with another element, in this case chlorine, and hydrogen with another element, in this case fluorine. So to indicate that it's a two-element acid, you have hydro at the beginning and ic at the ending. Now, the one thing I would like you to be aware of is notice this AQ. Please be aware, in this case, that these substances need to be in water to be considered an acid, to have these characteristics of being sour, conducting electricity, and so on. because if they are not dissolved in water, then what happens is these characteristics don't exist. So that's why when you're talking about acids, you need to put the symbol AQ, means that it's dissolved in water, before it will have these characteristics to be considered an acid. Okay? Now, a lot of times you will see the AQ is not written, and that's because a lot of times HCl or HF can only exist as solution. So a lot of times in some of the chemical bottles that you use, you won't see it. Okay, but technically you should write the AQ. Now for polyatomics, what that is hydrogen with a polyatomic. And that's what we call a polyatomic acid. So what happens is that depending on the ending of the polyatomic, notice ATE ending. If it's an acid form because of the AQ, it's just IC. If it is an ITE ending, it ends in OUS. Like hydrogen sulfite and sulfurous acid. Now, notice in this case, the key difference here is no hydro beginning. Okay, there's no hydro beginning. Unlike the two element acids, notice it says hydro and ends in ic. When you have a polyatomic acid, it's just ic or us ending. Now, you might say, well, Mr. Chan, what would be an example of the difference between the two? So let's say, for example, here, I'll give you something that you are familiar with. So let's say we have hydrochloric acid versus chloric acid. Now, the names look familiar. Okay, they look similar, but in this case, I know this one would be HCl, while this one would be HClO3. Now, how do I know hydrochloric acid is HCl? Is because you look at the name. There's hydro in the beginning and ic at the end. So what that means is that it's a two-element acid. In this particular one on the left, notice there is no chloric. There is no hydro for chloric acid. It's just chloric acid, no hydro beginning. Okay, so in that case, that is a polyatomic. And the ic ending here means that the polyatomic ends in ATE. So there, this is why we have the chlorate ion. Okay. And bases is just hydroxide in the name. Now, why is it always like NaOH or KOH? Is because since OH is a negative ion, remember in chemical naming, the positive ions are generally written first and the negative ions are written second. So when we talk about bases, we don't have to worry about, oh, is it ic or ite or whatever? It's just straight naming. Now, most of this should be reviewed, all right? And so that's why I've gone through it a little bit quickly. Now, what I'd like to do is move on. And we talk about acid-base definitions. Now, back in Chem 11, when we talked about acids and bases and this idea of having H plus in the equation and OH minus 1 in the equation for bases, what that is actually called the Arrhenius theory. This is generally what you focused on back in Chem 11. Okay, so what happens is in the Arrhenius theory, the acid is a substance that dissociates in water to produce H plus. Now, H plus is another term for that is protons. So what you did back in grade 11 is you'd be like HCl is an ionic compound, so it breaks apart to H plus and Cl minus 1. For a base, it is a substance that dissociates in water to produce hydroxide ion. The key word in those two, in this example, is that it dissociates. All it does is that it breaks apart. So in this particular case, for a base, it would be like NaOH breaking apart to Na plus and OH minus 1. Now, but this definition is kind of narrow. The reason being is because there are substances that have base characteristics. Remember the base characteristics up here is that it tastes bitter, conducts electricity, or feels slippery, but there is no OH in the formula. An example of this would be like Windex. If you take a look at Windex, Windex is a window cleaner, but what happens is if you look at the ingredients, there is no sodium hydroxide. The cleaning agent in Windex is NH3. So the question would be, how is NH3 able to have base characteristics, but there is no OH in the equation? So a new definition was developed. And this is what we're going to be focusing on in Chemistry 12. What we have is a Bronsted-Lowry theory. Now, here, the Bronsted-Lowry is an acid is any substance that donates a proton in an aqueous solution. Okay, please make sure you know the difference between dissociates and donates. So in this particular case, let's say if we were to use HCl, in this case, when it reacts with water, what happens is the H plus is given to the water. So what you have is you have H3O plus and Cl minus 1. This is the definition of the acid. Now, if you take a look at the products of both the Arrhenius theory of the acid and the Bronsted-Lowry theory of the acid, you notice the chlorine ions are produced. But while one produces H plus, the other produces H3O plus. Is there a difference? The answer is no. So H3O plus is called a hydronium ion. And this is a protonated water molecule. So a protonated water molecule means that it just has an extra proton. Now, when you're doing chemical equations, all right, in this case, what happens is the H3O plus has the same characteristics as the H plus when considering equilibrium expressions and can be used interchangeably. So when you take a look at this, HCl using the Arrhenius theory and HCl using the Bronsted-Lowry theory, they both produce a proton. So the Arrhenius theory is just H plus. The Bronsted-Lowry, we are acknowledging that the proton is donated to water and joins with water. But the characteristics of H plus and H3O plus are the same. One is just representing the Arrhenius theory. The other is representing the Bronsted-Lowry theory. Okay. Now, for bases, is any substance that accepts H plus is a proton acceptor. Now, what we can do is for NH3, what happens is that when it reacts with water, it can accept a proton from water. And so what you get is you have NH4 plus and OH minus 1. Now, notice now, what happens is that it sort of reconciles with the Arrhenius theory of a base. Notice you are producing OH minus 1 using both equations, all right, or both definitions. All right. Now, some of you might say, well, Mr. Chan, how would sodium hydroxide be explained using Bronsted-Lowry? So if we were to use sodium hydroxide using Bronsted-Lowry, what would happen is this. The first thing you have to recognize is sodium hydroxide is an ionic solid. So breaks apart to sodium plus 1 and OH minus 1. And then the OH minus 1 will react with water, accepting a proton from water to give you water and OH minus 1. Now, you notice this second equation is kind of redundant. So that's why a lot of times we omit this second equation and just say sodium hydroxide produces sodium ions and OH minus 1 for Bronsted-Lowry. Now, in these two examples, notice water is accepting a proton from hydrochloric acid and it's donating a proton for NH3. So in this case, water acts as a base and acid. When a substance can do both, it is said to be amphiprotic. Okay, when something is amphiprotic, that means it can either accept or donate a proton. Now, there is another general term for a substance that can act as a base and an acid. It's called amphoteric. Okay. Now, so an amphiprotic substance is a substance that can act as both an acid and a base, accepting a proton or donating a proton. You should be familiar with some of the terms. So if I were to use a monoprotic, monoprotic means one proton because of mono. Diprotic would be 2 protons. Triprotic would be 3 protons. So if I set a monoprotic base, what that means is that it can accept 1 proton. It accepts because it is a base. Monoprotic means 1 proton. If I have a diprotic acid, that means it can donate. That's what an acid is. Diprotic is 2 protons. So please make sure you are familiar with those terms. Now, when we talk about acid bases, one of the things is we have to consider is something called conjugate acid-base pairs. Generally, acid-base reactions are reversible and an equilibrium state occurs. So let's say we have NH3. So when we have NH3 plus water, what we have is an equilibrium system where the water donates the proton to NH3. So what you have is you have NH4 plus and OH minus 1. Now, in this case, in this forward direction, NH3 is the base, while water is the acid. Okay, why is because NH3 is accepting the proton while water is donating the proton, and that is going in this direction. Now, if we look at the reverse equation going from products to reactants, notice the NH4 donated to the OH minus 1. So in this case, NH4 would be considered the acid, and OH minus 1 would be considered the base going in the reverse direction. Okay. Now, this is stated in the next page. It says when NH3 accepts a proton, it becomes NH4 for the forward reaction. The NH4 plus ion is then able to give up a proton in the reverse reaction to OH minus 1. Therefore, in all acid-base reactions, there are two acids and two bases. Okay, one for the forward reaction, one for the reverse. A pair of substances that differ only by a proton. So a pair of substances that differ only by a proton is called conjugate pairs. So in this case, are called conjugate pairs. Now, so if we were to take a look at this equation and what are my conjugate pairs, in this particular case, NH3 and NH4 plus would be a conjugate pair, and you would have H2O and OH minus 1 would also be a conjugate pair because they only differ by a proton. Now, remember what is a proton? A proton is H plus. Now, one thing that I would like you to be aware of, notice, yes, they differ by proton. Notice is NH3 is an NH4 plus 1, and you have H2O and OH minus 1. What you need to be aware of is this. Note the change in charge. Notice what happens when we add or take away a proton. Notice the change in the charge. Okay, when you add a proton, not only do you increase the number of hydrogens, but you increase the charge. If you take away a hydrogen, what you do is not only do you remove a hydrogen, but you take away a charge. Now, one way I could ask a question regarding conjugate pairs would be something like this. Let's say, for example, I have HCO3 minus 1. Now, if I add a proton here, this would be H2CO3. If I remove a proton, take H plus away, I would get CO3 minus 2. Now, in this particular case, if we were to just focus on HCO3 minus 1, when I add a proton to become H2CO3, this would be considered my conjugate acid. If I take a proton away, CO3 2 minus would be considered the conjugate base. All right, so if I were to say, hey, what is the conjugate base of HCO3 minus 1? You take away a proton and you lower the charge and you get CO3 minus 2. That would be the conjugate base. And if I said, hey, what is the conjugate acid of HCO3 minus 1? You add a proton, so it becomes H2CO3, and you increase the charge by 1. Now, if you really wanted to understand the reason why, you could think of it like this. Why is H2CO3 the conjugate acid of HCO3 minus 1? The reason being is the H2CO3 is the conjugate acid is because it has to donate one proton to become HCO3 minus 1. And because it has to donate a proton, that's why it's considered the conjugate acid. Why is CO3 minus 2 the conjugate base? Is because CO3 minus 2 has to accept a proton, that's the definition of a base, to become HCO3 minus 1. Okay, that is using the vocabulary terms, but if you are just saying, oh, I just want to get through this, when I say, oh, what's the conjugate acid of a substance? You add a proton and increase the charge. If I said I want the conjugate base, you take away a proton and you decrease the charge. All right, folks, that is it for today. And if any questions, feel free to come and see me during class time. Thank you very much. Have a good day. Bye-bye.